Well, Dave, good morning. Welcome back. So, today we are going to continue our discussion on execution level control in the subject mathematical foundation of robotics. Okay. So, if you remember, earlier we discussed about the second order system because that is very common in modeling a control system, right? Today we are going to discuss that in the process of designing controller, there will be several parameters, right? One such parameter, say this is my parameter, right? And there could be, it's very common that there could be performance measuring criteria. This is one performance measure, and they could be conflicting, or there could be a trade-off. For example, in aircraft design, you see, if it is a passenger aircraft, then stability is the issue, and performance measure will be done, for example, on stability, reliability, like that. But if the aircraft is a fighter aircraft, then maneuverability, maneuverability will be a great issue. And these two, actually, there is a trade-off between these two. If you have a system which is extremely maneuverable, then its stability will be in question. And if you want a system um, with greater stability, robust system, right, then maneuvering it will be a problematic. So this is an example, rough example I gave you, so that you will understand that in control system design, there could be conflicting performance measuring criteria. Here they have shown, this is Dorf book, very famous book, Control System Engineering by R.C. Dorf. Say, there is a performance measuring function M1 which varies with the parameter like this. Another performance measuring function M2 varies like this. So what it is telling, you see, if my parameters are very small, nearer to 0, then the performance M1 will be bigger, but M2 performance will be very poor. Okay, which is bad, isn't it? And also, if it is the parameter is in this zone is too high, then the M1 performance will be very um, low, and M2 performance will be very high. So none of them are actually desirable. So that's why we always need to optimize. So here you see where these two performance measuring criteria are cutting at a point, meeting at a point. So here, if I put my design parameters here, then what it is telling that, it has neither very poor performance measure in terms of M1, neither it is very poor in terms of M2. So we could select our parameters, control system parameters, on based on this issue. Okay. So this is why it is important, because always, you see, controller design is a very, very difficult task, and always, just I have shown you two, there could be many such criteria, performance measuring criteria, and you will have to optimize them, right, by understanding the problem in depth. So here are some control signal which are very commonly used for testing a controller. After you design a controller, you need to test it. How to test it? The test could be with the help of a step function. So this is called step function. So this is ramp function. This is parabolic function. So using these functions, and this is the definition of the step function. So RT equals to A constant for t greater than 0. And then it is 0 if t less than 0. Okay, time less than 0 is not possible. So that's a step function. That's the definition, right? And you know, if I, after designing a controller which is behaving just like a second order system, then you can just now understand that out of this three criteria, this is, say, critically damped, this is say underdamped, and this is say overdamped. Okay, out of these three, which one is preferable? Obviously, critically damped. Why? Because I have asked controller to at t equal to immediately at t equal to 0, means as soon as it starts, I am asking my controller to move A, and this is called settling time, and within very less time it is obeying. So that's why critically damped situation is, time and again I told you that it is preferable criteria based on which the control parameter um, could be designed. Here also ramp function can be also used for testing. So this is, you see, if this is underdamped system, then this is called transient response, and then as soon as it becomes like this is called steady state response of the system, because you have stiff, so you have an external excitation with stiff function. So ultimately in the steady state, the controller will attain that state, okay, based on parameter which makes whether it will be critically damped, or if it is underdamped, how many oscillations you will allow. Okay, you will have to design such a way that not many oscillations, if at all underdamped system is unavoidable, then use like this, okay, so that very quickly it will stabilize. So all these issues are very intuitive and very common in control system parameter designing, okay, because after designing you will have to test. So this is a testing signal called stave. Similarly, ramp is a testing signal. So this is say critically damped, and then underdamped, and this could be overdamped, okay. So again, so ramp will be in the steady state, the controller should follow it, and similar is the case of parabolic testing signal. But most commonly used testing controller testing signal is stave, okay, stave function. Also, I need to tell something about your control system reduction, because in actual practice controller design there are so many systems, subsystems are there, okay. So it's very difficult to visualize a complicated control system consists of several. You can imagine, right, if you are trying to design a aircraft controller, how many hundreds, if not thousands, subsystems are there, and many of them have their transfer function and all kind of thing. So we need to simplify, and there are so many methods for simplifying. These three common methods I have given. One is cascading the block. For example, I have G1, G2. So these are our transfer function. Okay, this is input. Okay, this is output. This is again input to this transfer function. This is output. So equivalent will be G1, G2 with input X1 and input X3. Okay, how you look here. Right? So X2 by X1, that is output by input, equals to G1. You can put it S also, because normally we operate in the frequency domain. So this S is the S parameter in the S plane, right? So this is actually the definition of transfer function. This is the transfer function. If it is a motor, then all the mathematical relations are there. It could be armature current, and their output could be torque. So this will give me X2 equal to G1 into X1. Okay. So now this is actually input to the second block. So what is G2? G2S will be output by input again. Output by input equal to X3 by X2. Now X2 equal to, in terms of input signal, this, right? So we'll write that G1S into X1. So now, which is actually, so G1 S into G2S times x1 equal to x3. So again, final output by initial input is equals to G1S times G2S. So this is called cascading. So if I just, now this is what? This, okay. If I consider input as x1, then if I want to replace many such transfer function, then they will be cascaded, they will be multiplied, okay. Is it clear? Very simple, right? So in the resultant block, x1 is input, g1, g2. Similarly, you can extend it, just making, to avoid symbolic complexity, I am just omitting s. Suppose we have so many g2, g3, up to gn x1 xn. So output, in this case, output by input will be g1s, g2s, blah blah up to gns. So simply they will all be multiplied. So this is the rule of combining blocks in cascade. If my blocks are like this, then resultant block. So you can just replace this by this one, G1, G2, G3. All multiplication you can do, and then you put them in a block. That's a function block. Then this is x1, and this is xn. Okay? So this is what? This is very important. Right? Then also, you see, normally the controller are closed loop control, as we have discussed, and there is a feedback loop normally. So say this is say x2. So say x1 is the input signal. So there is a junction block now, right? And then in case of this is very, very commonly used control system feedback loop. Okay, so there is a transfer function, then there is an output x2, then you are taking some signals from the output, then feeding it to another transfer function h, and then you are either positively feedbacking or negatively feedbacking, although negative feedback is very common. Then what will happen? This is equivalent to this. You can analyze it very easily. You see, what is it? I will do that. So what is the signal here? So x1 is coming from this junction. Then x2 time h is the signal here. So h, x2. So here actually you are having, depending on plus or minus as it is, you are having h, x2. Okay. So this is what you have. Times g. So this is the signal of the, so this is the signal, right? Times g is equals to your x2. Clear? Very clearly understood, because this is very simple, right? So you have a junction block where the input signal is x1, and then you have output x2 signal, and through some sensor you are taking the feedback, okay, and feeding it to a block, okay, so it could be a sensory block, transfer function, okay, and feeding it back, so that, so this is also known as error actually, in control signal, this is error. So it's an error driven system. As long as error will be there, that means your desired output is x2. So when desired output x2 will be there, when error will be 0. So we will try to make a control law so that error will be 0. We will discuss that. But here I am trying to tell you that this circuit which is otherwise complicated to see, okay, look at it, is very simple, okay, in this form. So these and these are equivalent. From here I am getting this, you see. So this is x1 equals to, so x2, and take this here in this part. So this is a plus minus. So if I send on the other side of the equal sign, then plus will be minus, minus will be plus. So, and then I am taking common, right, here. I am putting it here. So very simple manipulation. 1 minus plus g into h. Okay? So this is what it is. And then what it is telling you that what will be our x2, x1 into g, right? Sorry, so x1 into g plus gh, had it been here, but I have taken it on the other side. So plus become minus, minus become plus, okay, and gh, so gh minus plus gh, x2 by x1 equals to g1 minus plus gh, okay. So this is what it is. So this is similarly moving a summing point ahead of a block. So you see, suppose I have a summing point here. So, and this is input signal, this transfer function, this is output signal x2, and this is another signal which is coming from somewhere through feedback loop. Okay. So if this junction point requires to be here, then what changes will be there? You see, just simply you will have to put x2 and g instead of g, 1 by g, you will have to feed it back. Say this is equivalent, right? See how. So here what is the signal? Here signal is g x1 plus minus x2 equal to x3. Okay. So am I correct? So x2. This is, and here what it is? Let us see. Here signal here is x1. Here it is plus minus x2 by g, okay, times g equals to x3. So x1 g plus minus x2 equal to x3. So this and this, they are same, isn't it? So this circuit with a junction block ahead of this transfer function block, if I would like to take it back here as it is shown here, then simply I will have to do with x2, I was putting in this case straightway, but here x2 has to be fed through a junction block or through a transfer function 1 by g. So g, if this is g, this will be 1 by g. Then yes, you can do that. This junction block can be put ahead. And like this, there are some more tools so that in case of a giant system, you can reduce it in the form of in the form of a transfer function, okay, g1, g2, g3, okay, and x1, xn. So our main objective is how to all this complicated control subsystem can be represented in the form of an equivalent. This is open loop. You see, there is no closed loop, nothing. I have replaced everything, right? So after simplification, so um, this is the aim or objective of simplification, so that you can write your control, otherwise complicated control system in the form of a simple one. Okay, so this is called block diagram reduction. There is another tool in control engineering you will study. It's called signal flow graph. So the signal flow graph is another alternative tool. Instead of block diagram representation, you can represent a complicated control system in the form of a signal flow graph. And graph is very easy to represent in computer. So after representing the control system in the form of a signal flow graph, then using Mason's rule, you can actually reduce the control system. Okay, so either way, use block diagram or signal flow graph, the basic objective is same, that I want my control system should be simplified, and these are the tools which can do that. So after telling all this, now let us try to concentrate on how to control a second order system. So throughout my few lectures, I have introduced you with second order system behavior, and in the very beginning I told that if I know somebody's behavior, then only controlling that particular guy in case of human, it is easy, right? And in that context, initial lecture I told that since your behavior, children behavior may be known by parents very clearly, so parents can control them effectively. So similar is the case, if I understand the behavior of a control system, and in many of the cases the control system is modeled as a second order system, so if I know the behavior of a second order system, then I can control effectively. Okay, control means what? A system parameter I can tune so that there will be no oscillation wherever I want, whichever state I want control should follow it with immediate effect, it should go there. So this is the basic idea of controlling a system. So I will now tell you how to control a second order system, because second order system now you are conversant with, and second order system is enough for actually modeling my robot. Okay, so say this is again mass spring damper system, this is and here you see I am now putting a force F. Why? Because I want at t equals to 1, my block will be say at x1. At t equals to 2, t2, my block will be at x2. Like that. So at tn, my block will be xn. If I want that, I'll have to put some excitation or force, right? That will ensure this. Okay. So this is that force. Okay. Say this is the force which is not yet known to me, which will actually be able to control a mass spring damper system. So this is the damper model. This is spring. This is mass. Okay. Sorry, this is actually C. Okay. So this is I'm referring your textbook, that is John J. Craig's. You can also visit that. Now let us try to understand amx double dot plus cx dot plus kx equal to 0 if had there been no exciting force, but now I am controlling it. So if I wanted to study the behavior, there will be no force, right? So equal to 0. But now I will control it. So this is my F is my control force. Okay. So see, I have now represented this in this form, that suppose this is my system, it could be robot system. Actually robot system means it's motor. Okay, basically joint motor, and each motor can be drawn like this. Okay, so this is my system in general term, and I am actually now forcing the system with this force F. And suppose what I will get if I apply force, I will be able to move m somewhere and say somewhere is x with some velocity and say that velocity is x dot. So this is those state parameter x and x dot because I have now applied force. And now say I have a junction block. Okay, so this is a representation of this. This is a mathematical representation of the controller, and this is a schematic diagram of the controller. Try to understand it very clearly. Very easy. So what I am trying to do, output, and I have decided that I will take both signal x and x dot to effectively control. This is that is my control force will be proportional to the x state, right? Displacement x and x dot, that is the velocity. That is my decision. So I will have to just see, okay, as a result of f, where it is going at what force, and then I will have to have those quantities, and I am putting some gain. They are in control terminology. They are called gain parameter. There are some parameter. Kp is actually x is fed with Kp. So here Kp into x is the signal. Here Kv x dot is the signal, and negatively feedback I have given. So f is equals to minus Kv x dot minus Kpx, right? So this is the signal. So f equals to, so f is the signal which is going out from the junction. These are the two signals coming into the junction. So f is equals to, so input signal equals to output signal, right? So f is actually equal to minus Kv, because minus feedback I have designed. So this is my design, okay? And my basic objective is to control the block. And I have done this. Now, if I write now the system with control, you see, equals to minus Kv x dot minus Kpx. By the way, the formal term of this type of control is known as PD control, proportional derivative control, very popular. Derivative. Proportional derivative control, okay? Controller. Now, if this is my equation, then how can I simplify it? Mx double dot plus, I am taking this here, C plus Kv into x dot plus K plus Kp x equal to 0. Now you see what is M, C, K, they are the system parameter, right? Once the robot is given, or robot mass is given, damping, joint damping is known, and K stiffness of the link is known, like that. Okay, in mass spring damper system, so these are called system parameter. And x dot, they are state parameter, right? So you see, both the system parameter and Kv is the gain. Kp is the gain, which is a parameter, constant parameter. Okay. So for linear time invariant system means C is not varying with time, neither M nor K. So I can write Mx double dot plus x dot plus equal to 0. So this is again a second order system, and you know, if I want my system should be critically damped, put in critical damping condition. What is that? Under discrimination root, C prime square for AC, right? M, K prime. So this has to be 0. So what is that? Equal to 0, and c prime square equal to 4 m, and c prime equals to 2 root over of m k. Now, so if I design kv, so what is kv? I cannot do anything with c because system is given. I can only manipulate with kv because that is the controller design I am doing. Okay, gain parameter. So I will select kv in such a way that this becomes 2 root over of m k prime. Okay, and within k there is one parameter k which cannot be, it's not in your hand, it cannot be changed, but kp again can change. So changing kp and kv, by manipulating kp and kv, I can reach this condition. And once you reach this condition, then this controller is PD controller. And what you will achieve? You will achieve this. You see, say at t. So at t1, say you want. So this is x and this is t, right? So at t1, you want controller to reach x1, right? So t1 x1. So it should be at t1 like critically damped. You have by manipulating this parameter. So you will see that within t1 time x1 will be accomplished. If you want at t2, your block should be at x2. So this is your x2 group. So with t2, you can start from somewhere and block will go under critically damped condition. Okay, it can be achieved. So this is, I wanted to tell you intuitively that this is a proportional derivative controller which can control the block position as per your desire. Okay. Now we will see that is it a good controller, because controller you will have to design, spending a lot of effort, a lot of money. It is not a good controller. Why? Because you see, this is not portable. I mean, this controller is specific to control a particular system like this. I do not want that. So in the next class, I will tell you that why this controller is not good and how we can design a better controller. Okay. And you are right. I am going to discuss a very important concept in control system design, which is called model-based control. And in case of robot, it is also known as, in motor control, it is known as computed torque control. So there are so many names. In the next class, I will start from here that I am trying to design a controller. I designed a controller which is controlling my system, but I am not satisfied with that. The reason is it is specific to this particular system. If I want the same controller should be able to control another system, it will not happen. You will have to redesign it. So that's the problem with that, and that's why model-based control one should practice. And in the next class, we are going to discuss in detail about model-based control. But prior to that, I can take an example, concrete example, to show you that this is actually problematic. The naive controller which you have designed. But nevertheless, you have understood that what is a PD controller when the output are being compensated, taking output state x and x dot are being compensated by attaching two parameters kp and kv. So you have 2 degrees of freedom. You have option to select kp and kv. Show that your system is controllable. Okay. Thank you for your attention. So controller design is intuitive and it is very, very nice, and it is very, it's a rather art which we express in the form of mathematics. It is rather art to design a controller. Okay, that's why in the world, knowing all these tools and techniques, very few companies are there who has monopoly on controller design. Okay. You can Google who are the companies which can produce good controller for robotic application. So next we'll talk about model-based control. Till then, stay safe. Have a nice day. Bye bye.